In this lecture, we're going to talk about potential dividers, variable resistors, and sensors. Previously, we've already covered kind of the basics of electricity, current, voltage, resistance, Ohm's law. We've also drawn and solved unknowns in complex circuits using our understanding of series and parallel, as well as combination circuits and Kirchhoff's laws, all applying these relationships involved. And we're going to continue to use these relationships and just look at how we can sort circuits out to help us understand the VI characteristics, the voltage current characteristics of different components such as lamps. We're also going to use these to help us kind of divide the voltage to what we want it to be in a circuit. So we're looking at sub-objective number 3, really just describing the practical uses of potential divider circuits, including the use of sensors. So a very basic potential divider circuit is something where we have some voltage coming from a battery and 2 resistors. And we know that according to Kirchhoff's second law, that the voltage that's provided is going to be distributed amongst V1 and V2. So let's say we want a specific voltage in V2. So with a 4 volt input voltage, we want our 6 ohm resistor to have a 3 volt output. So what do we need R1 to be in order for this to occur? There are 2 ways of solving this. Let's do it kind of the long way, and then we'll do it the short way. Both are fairly similar in length. But I do know that similar to what I did before, that this 4 volts is going to be equal V1 plus 3. So that tells me that my V1 is going to be 1 volt. Now, when we look at a circuit, we want to try to identify any values kind of that we can solve for immediately. So I'm going to first think of my voltage is equal to IN times RN, and focusing on the second resistor, where I have 3 volts is equal to my current across that resistor, what's called I2, times my 6 ohm. And that tells me that I2 is equal to 0.5 amps. Now, we are in a series circuit where the 2 resistors are in series, so the current that's passing through right here is going to be equal to the current passing through. Let's do that in green. It's equal to the current passing through right here. So I2 is just I. There's no I2 in this case. It's just I. So we know that the current 0.5 amps is also passing through R1. We know that that voltage has to be 1 volt. So I can also say, well, V1 is equal to 0.5 times R1, and V1 is equal to 1 volt, so 1 is equal to 0.5 times R1, and this tells me that R1 is equal to 2 ohms. Now there's another way we can do this. It's a potential divider. That means the voltage is being distributed, and we do know that the voltage in a series circuit is proportional to the resistance, given that the current in a series circuit is the same across all resistors, or all resistors that are in series. So when we look at the 6 ohm resistor and the 2 ohm resistor, we may notice that the 3 volts is 3 times the 1 volt, and the 6 ohms is 3 times the 2 ohms. So this is the whole proportionality. So we can also similarly see, well, like V over R is equal, like V1 over R1 is equal to V2 over R2, because we know that that equals the current I, which is constant. So we can see this as, well, 3 divided, well, I guess we don't know we don't know R1, so this is 1 divided by R1, because that's 1 volt in V1, is equal to 3 over 6. 3 volts divided by 6 ohms, and if I solve for this, I would get R1 is equal to 2 ohms. And these are the 2 separate ways that we can solve this problem. Recognize that this particular way, when solving for resistances, only occur in series because the voltage is proportional to resistance. In parallel, because the voltage is the same in each branch, this way doesn't work, but there is probably a similar way to solve for the currents inversely proportional to the resistance. So we use these in particular circuits in conjunction with variable resistors, and we're going to learn about other types of resistors. In case we want to kind of adjust the total voltage that we are sending to this, like for example, a variable resistor. So this, we'll put in a fixed resistor, and then because of the fixed resistor, the variable resistor cannot reach a too high of a voltage. I'm going to show you an example of one of these. So I have my phone charger, the one I plug into the wall, and every one of these, you should see an input and an output. And the input, for example, would be like somewhere between 100 to 240 volts. So in this case, right, 220 volts is coming into the outlet. And our output would be, in this case, 5 volts, 2,500 milliamps. So there's something in here that acts as a potential divider, where you have a variable resistors, you have maybe some other types of resistors, to where we end up with only 5 volts and 2,500 milliamps output. So we want to, it controls how much voltage is being sent out. Now, of course, this is probably a lot more complex than the type of circuits I'm showing you, but it is an example. And we're back. So these can be used in circuits where we don't want to overload the voltage going to one of the resistors. We want a varying voltage. We can use this variable resistor and a fixed resistor. So let's ask ourselves, what range of voltage can the variable resistor have, and what range of voltage can the fixed resistor have? So let's decide on our boundary conditions for this system. The boundary conditions are the minimum and the maximum resistances involved in the variable resistor. And I might want to draw two separate circuits, one where we have maximum voltage and one where we have minimum voltage. That's a resistor. In our variable resistor. So in this case, this is like 0 ohm, let's say, which means it doesn't actually exist. I don't need to draw it, but I'm including it just to recognize that it's there. We have 2 volts. And then in this case, we have 10 ohms, and our maximum would be 10 ohms. So as I look at, let's just move this apart. Let's look at the voltages that exist. In this case, the 0 ohm resistor doesn't apply any voltage, because voltage is proportional to resistance. So it's V equals IR. The 0 ohm resistor has 0 volts. Therefore, all of the voltage goes to the 10 ohm resistor. And when we have a variable resistor that reaches 10 ohms, then, well, the 2 volts is going to be split between both 10 ohm resistors. So this is 1 volt and 1 volt. So in our fixed resistor, we have a voltage between 1 and 2 volts. In our variable resistor, we have a voltage between 0 and 1 volt. So this is just a basic example on how we can use a variable resistor to max out the voltage that's applied to the variable resistor. And these variable resistors look like this, which is in our data booklet. And an old version of a variable resistor, it can look like this. We have one in my classroom, but this is actually kind of a pretty big. It's about 20 centimeters long. And of course they are old, so we don't really use them. But if we were to kind of imagine there is a battery attached right here, and maybe there's a lamp right here, and it's connected onto this little pole. And that means it is connected to this coil of wire somewhere in the middle between what this shows as low and high. This whole wire coil is 100 ohms. But what we're doing is we can move this left and right. And when we move it left and right, we are increasing the resistance applied in the circuit. At this moment, it's connected right here. And that means it coil, and then eventually comes out. And then that's the resistor. That's the variable resistor in this circuit. And if it's like, between here and here, who knows, this might be like 30 ohms. And as we move this position left or right, we're decreasing the resistance or increasing the resistance. So this is an old version of a variable resistor. We're going to look at new versions of variable resistors, which are called something slightly different. And we're going to also look at other types of sensors that its resistance get affected by different things. The first one we're going to look at is a light-dependent resistor. this light-dependent resistor, as a light intensity is incident on it, the more brightness that it feels, the less resistance it has. And this is useful, particularly in our phones. One thing you'll notice is your phone's changes the brightness level depending on if you're in a dark room or let's say if you're outside in the sun. So what it's doing is those sensors up on the top left of your screen have light incident on it. It's changing its resistance. There must be some process that the phone does to read the resistance or read the voltage applied to the LDR, and then determine how bright it is outside, and then change the brightness level of the screen to best support, us viewing our screens. That's one version of light-dependent resistors. There are others as well that can be used. The next one we want to talk about is a thermistor. Different than a thermostat, but very similar. So these things can exist inside of this, in our air conditioning or heater, where if we turn it on, we say, hey, we want the temperature to be 24 degrees Celsius. And so the thermistor will read the temperature that is in the ambient temperature. And if it's greater than 24 or less than 24, it might turn on this air conditioning unit or heating unit. So again, similarly, it reads the temperature its resistance changes based on the temperature. There must be a voltmeter or somehow it reads the voltage across this thermistor to help us determine what resistance it has, and then determines the temperature. And then must be some process, again, programming involved to make this happen. So one thing, both as brightness increases or temperature increases in a light-dependent resistor or a thermistor, the resistance will decrease. So in this question, in the circuit below, which of the following will cause the greatest increase in the reading of the voltmeter? We have a 12 volts being applied across these two resistors in series. The voltmeter doesn't really exist. It doesn't affect the circuit. It only is there for us to measure the voltage across this other resistor. So we want a greatest increase in the reading of the voltmeter. Now, the answers that they have relate to temperature or light intensity, so we just need to remember in our data booklet what type of sensor are we looking at. This is a light-dependent sensor. And so then we know that it can't be temperature or, let's use like red, it can't be A, can't be C. So it's either B or D. So the question is asking the greatest increase in our voltmeter. So if we want this, let's call this V2, right? If this V2 to increase, in order for that to happen, that must mean that V1 has to decrease. For V1 to decrease, because we know that voltage is proportional to resistance in resistors that are in series, that means that this resistance has to decrease. How does resistance decrease? Well, it decreases when the brightness moves forward. So we know that we have an increase in light intensity in order to decrease the resistance, to decrease the voltage that's provided to the LDR, and then the V2 will increase. So the answer is B, an increase in light intensity. Therefore, light intensity increases. All right, let's look at our last component that we're going to look at. It's called a potentiometer. It's a fancy word for another variable resistor, but it's used more often to kind of divide voltage. It has a circular knob that rotates left and right, and there are 3 terminals. The 3 terminals are connected to the outsides of this resistive film, so all of this is like one big resistor. But we have the ability for a wire to kind of connect and touch this point, and what it does, it creates a junction right here, because this wire will come down here and connect to point B. So there is a resistance between A and B that connects here and all the way here, and then there is another resistance that connects between, if I were to kind of imagine another line right here, between B and C. And when you add these up, we just get the total resistance between A and C. But it's important to recognize that there is a junction right there that kind of breaks up between A, B, and C if we're using all points A, B, and C. So let's look at how this can be applied in a circuit. So in the diagram, we have 0 kilo ohms going between A and B. And we have all of the resistor, all of the potentiometer in series because there is no resistance occurring in this parallel because the connection is happening right there. So that means that between points A and B, there's no resistance. So that must mean that I am moving this all the way down, and I have a point that's my arrow is pretty much right there, and that means that between A and B, there is no resistance between A and B because it's not touching any of the resistive film. So if I were to draw this out, kind of how this would look like, this B would come down. I would have a lamp right here. That's assuming like this would be connected to a lamp right here. And that would be in parallel. The point AB would be in parallel with this lamp, and that would be connected to a battery. I'm doing it. And then we'd have this green is happening right here. So actually, let's do this in all red. Because this red portion that's right here, between that is what we're observing in this 0 ohm connection between A and B. And then the rest of the resistor would be this part that's in complete series outside of the lamp. Now, the big takeaway is that just we have 0 kilo ohms, and as we turned the knob all the way to the left, there's no resistance across this between these 2 points A and B. What if between A and B we have some? So actually this is like right smack dab in the middle of this resistor. We have to imagine there is a point C right here. That means that only some of the resistance is in series, and it's half. It's about half. So it's imagining that like this is connected and it's at about half. So let's kind of connect this point right here, and we can see that some of the resistance, and so let's kind of get rid of this, it doesn't exist. Some of the resistance is going through here, like that's some of the resistance that's going down, and that's again going to a battery. This point B is coming down, and it is connecting to the lamp. And there's a battery, let's do that in black. And then the green's right here to connect this point. So we see that the points between B and C, the portion on the right side, is in parallel. And then we have a junction, although it's kind of weird to see, but there's a junction right there. Let's do that in like shiny greens. There's a junction right there. And then we have the red portion, this portion, this red line going all the way down, which has some resistance, is in parallel with this point, this lamp. And that's this section right here. Right, if we had to imagine there's a lamp connected to this point between A and B, and then the rest is the resistance that's in series. All right, so the next step is what if it's all the way across? So pretty much B has been moved all the way to point C. We can imagine like this is point C over here. So that means that this arrow going down is connecting here. And we still have that lamp connected. We have the battery. And then we have this point C. Now, as we can see, between B and C, there is no resistance. So this line would connect right here. This right here would have 0 resistance going through because it does not pass through any of the resistor to connect the lamp right here. That means that all of, and there's, of course, like I said before, there's a junction right here. And so all of the resistance in this potentiometer is in parallel with the lamp. So this right here, all of that goes down right here is in parallel with this B portion. And that's drawn better in this circuit diagram, as can be seen a lot more. So these are, as we move the line, the arrow between between the left sides of between pretty much point A to somewhere in the middle to point C, we are adding resistance in parallel, removing resistance in series, and vice versa. So now let's apply this understanding to practice. We have a potentiometer and a lamp connected to a 4-volt battery. The potentiometer has a maximum resistance of 10 ohms. We want to imagine that there's the potentiometer is, the arrow is turned all the way counterclockwise to where it's connected to point A, as we've seen above. We also want to calculate the voltage when it's connected at B, and then we want to calculate the voltage connected at C. So how much voltage can be applied to the lamp when all of the resistance is in series, half in series, none in series. So first, let's draw. I want to redraw each one. Let's say connected to A. So let's do part 1 where it's connected to the A. I have a battery, 4 volts, and then we have a full-on resistor. All of the 10 ohm resistor is outside of the lamp's parallel. So this is all 10 ohms. And then we have the arrow is technically connected right to the bottom, but I like disconnecting a little bit and making its own parallel circuit. And you'll see what happens here. And this is why when we said there's 0 ohms connected right here, how is that going to play out in this circuit? Like where does the current go when you hit a junction that doesn't have a resistor in one of the branches? Remember, current goes the path of least resistance. All right, so that's part 1. That's the connected to A. Let's do part 2, and we're gonna calculate the voltage after we do each of these. Part 2 is it's connected right in the middle. So we have a 4-volt battery, and then it's split. It splits the potentiometer up as if it's like cutting it right in half and creating 2 separate resistors. One that's in series with the battery and one that's in parallel with the lamp. And so that means that the lamp is connected right here. And then now we can see the lamp has a voltage that's going to be read. In part 3, this is the one where all of the resistor, well, in this case 10 kilo ohms, is in parallel. So we have pretty much circuit looks like this. Because the arrow is connecting right here, which means it's point C, right? This point is the same as this point, so we can just imagine this goes out and connects right there. So these are the 3 circuits. Let's put in all our values. This is 10 ohms. This is split right halfway, but it could be anything. It could be 4 and 6, 3 and 7, but in this case, I put it right in the middle. So this is 5 ohms and 5 ohms, and then I think the lamp is also 5 ohms. Yep, lamp's 5 ohms. Let's write that in there. Once we have understood how this potentiometer splits this resistor up and creates these 3 circuits, this is nothing different than what we've done before. This is just looking at series and parallel or combination circuits and applying our understanding. So I'm gonna pause this video. I'm gonna work out the math. I want you to do the same for part 1, part 2, and part 3, and let's see what we get for the voltage in each of these together. Remember though that in part 1, the current goes the path of least resistance. And then you might be able to think of how Kirchhoff's laws can be applied. Like, what does this loop actually do to make sense of if there's a voltage in this lamp. Okay, I'm going to pause. Complete this work. All right, we'll start with the first one, recognizing that as we hit the junction, the current's going to go the path of least resistance. So since there's zero resistance in the branch with 0 ohms, all of the current's going to bypass the lamp, and the lamp will have no current traveling to it, meaning there's going to be 0 voltage applied to the lamp. The next one gets a little tricky. This is, of course, the hard one, where we have a combination circuit. So there's a couple of ways to do it. I simplified the circuit and combine the lamp and the 5 ohm resistor to where it has 2.5 ohms combined resistance. And I found my total resistance, I found my total current, and then I found my voltage in my lamp by just doing the current times the resistance, recognizing that the current is this combined current of the branch, and the resistance is the combined resistance of the branch as well. You can do this. And lastly, we have the lamp that is in perfect parallel with the 10 ohm resistor. Since it's parallel, we have 4 volts. So this 1, 2, and 3, we are moving the variable resistor, the potentiometer, so that it has 0 volts, somewhere between 0 and 4 volts, and all of the 4 volts. And this is a way that we can learn VI characteristics of this lamp. If we want to have a little bit more control of what voltage it is, this is the ideal type of circuit to kind of control that with the most control. If we wanted to redraw the circuit so that the current and voltage is measured in the lamp, so that we can determine VI characteristics, then we have our potentiometer right here, and it's connected to my lamp. Well, how do I determine my VI characteristics? Well, I need to know what my current is. My current is traveling through the lamp, and then we also need to know the voltage that is applied to the lamp. And this is how we would do it in a lab. Okay, so to kind of sum everything up, we started off with very basic potential divider circuits with 2 resistors in series, knowing the resistance. Then we said, well, what if we have a variable resistance and we can move the resistance between 0 and some ohms? That's going to control the voltage a little bit more. Then we said, well, what if we use this in specific situations, such as when light is incident or when temperature is increasing, to help us create components that help us control the brightness of our screen, that control the temperature in our house. That is how we use light-dependent resistors and thermistors. And then we said, well, potentiometers are also kind of useful. They are more complex variable resistors, and we can use them to control the voltage in a lamp or in a specific component if we connect it in this sort of way. And then we can also use this type of circuit to help us determine VI, so voltage current characteristics of a given component or resistor. That should do it. I will see you in class.